In the previous lesson, we imagined what would happen if you took a piece of fur and rubbed it across a plastic rod, giving it a uniform charge. Could you determine what's the value of the electric field at the point P identified? If we say point P sits at a distance A from the rod of length L. So if the total charge on the rod is capital Q, we found that the electric field is equal to K times the total charge divided by the product of A and A plus L. And we checked it for the case where L approaches 0 and found the result would be E equals KQ over A squared, which is the same thing. We could say KQ over R squared if we wanted to change the name of this to R. In other words, it was consistent with what we know about Coulomb's law. So to carry on in this study of finding electric fields for varying charge distributions, let's consider we take the fur, and this time we rub it all the way around this ring, giving it a total charge Q. We'll say the ring has a radius of, again, we'll use the symbol A, and this time we want to find the electric field here at point P, which sits at a distance of x from the origin. So we're going to have to use the same approach that we did for the rod. Imagine breaking it up into several little pieces. The very first piece here sits at x equals 0, the very last one at x equals L. And here we just identify one random one we call dq. So the same thing, we're going to divide this ring up into a bunch of little bits, and maybe we identify this one right here, we call it dq. Actually, the one I want to identify is the one sitting right here at the top of the ring. Okay, so we'll call that dq. The total ring has a charge, capital Q. This is our x-axis. There's the point in question. Nothing wrong with including our y-axis. There's also the z-axis. So what we need to do is picture what the electric field would look like due to just this little tiny piece of the overall charge. So we'll draw a line that connects that element of charge to the point in question, and the length we'll call R, and we know there's going to be a component of the overall electric field due to that piece. That's not the total field vector, that's just the contribution to the field from this charge dq. I guess if we also chose the little element of charge down here, which is also dq, then its contribution to the total field would be just as large in magnitude due to the symmetry of this arrangement. However, it would point up and to the right instead of down and to the right. Now you're going to have to use your imagination to think in 3 dimensions here, but imagine what the direction of the contribution to the electric field would be due to this dq. It's going to have a component to the right and then a component pointing into the screen, right? I can't properly draw this. Maybe we can say, like if we were to take all the electric field vectors, they sort of trace out the surface of a cone, right? So because of that symmetry, all of the components on the y and z axes are going to cancel out, and all you're going to be left with are components that add up along the x-axis. So if we want to find the total electric field in this case, we don't need to add up all the dE. What we need to do is add up just all of the x components of these contributions to the field. So let's draw this again one more time. Okay, so what we're interested in is this component dE subscript x if this vector is dE. So there's some angle theta here, which is the same as this angle theta. So I guess dE along the x-axis is dE cosine theta. But what is dE? Well, it's nothing more than k dq divided by r squared. And r is equal to the square root of a squared plus x squared, right? I labeled the radius of our ring A. I guess if I draw this line, that's also the radius A. So we've got a right triangle with side A and side X. Yeah. Or another way to say this is r squared is equal to a squared plus x squared, which is nice because we see an r squared here. So if the total electric field at point P can be found by summing up all of the horizontal components of each contribution to the electric field, and in step 2, we can say the total electric field is equal to the integral of dE cosine theta, or in other words, k dq over r squared cosine theta. Okay, we've got to make this calculus of a single variable. So E is equal to, we can take the k out at the very least, k times the integral of dq over, let's substitute and replace r squared with a squared plus x squared. And let's see, what can we replace cosine theta with? Well, cosine theta is equal to adjacent over hypotenuse. So we can replace cosine theta with x over a squared plus x squared to the 1/2 power. Same way as saying square root, right? To the 1/2 power. So E is equal to k times the integral of x dq divided by a squared plus x squared to the 3/2 power. Now wait, what's a variable and what's a constant in this case? So let's say we picked a different element of the overall charge. What if we picked this little bit dq here? Well, isn't the distance from that dq to point P, doesn't it have the same x value as this one? Won't any one of these dq's all have the same value of, well, they'll have the same value of a and of x, right? And of theta. It looks like, here I'll highlight them all in green, looks like x is constant, a is constant. Oh, so I can take all this out of the integral. So this is actually, looked like it was going to be more difficult than it really is. I believe we just get E is equal to kx over a squared plus x squared to the 3/2 power times the integral of dq. Well, that couldn't be any easier. The integral of dq is just all of the charge q. So there we have it. The electric field at point P is equal to kqx over a squared plus x squared to the 3/2 power. As always, let's check and see if this is reasonable. So let's take some special cases. Let's take the case where point P doesn't sit at some distance from the origin. Let's move point P all the way to the origin. Then that means x is equal to 0. But if x is 0, then the whole solution is 0. But don't we expect that? Yeah, if we have a ring of charge, and maybe it helps to just draw it looking with our eyeball straight down the x-axis, then we see the ring from this aspect. And if the point is right here, well, that bit of charge creates a downward electric field, but I can pair it up with that bit of charge that cancels it with upward field, and this bit of charge creates field this way, but it's canceled by this bit of, you see where I'm going with this one. Yeah, sure. The net electric field should be equal to 0 if x is equal to 0. Let's take another limiting case where A approaches 0. In other words, our ring becomes smaller and smaller and smaller until it appears that the ring is practically just a point charge. In other words, A can't effectively be 0, but it could be much, much less than x. And in that case, if we let A equal 0, then what do we have? KQX over 0 plus x squared to the 3/2 power. In other words, KQX over x cubed, which is KQ over x squared, which is the same as KQ over r squared if we want to rename our variables. So again, it agrees with Coulomb's law. So once again, it seems as if we've verified our equation as being consistent with the extreme cases. Fantastic. Hey, thanks for watching.